Hello, we are the NUWC team, the contactless recharge discharge of UUV batteries, and this was sponsored by the Naval Undersea Warfare Center, known as NUWC. I'd like to start off by thanking our technical directors, Peter Nickerson, who was the one that came from NUWC and worked with us throughout the whole year to help us get up and running a prototype for the project, and also Brendan, who is a software engineer that graduated from URI in 2017. For Meet the Team, I myself am Tucker Snow Gerard. I'm a graduating electrical engineer. And then there's also my partner, Isaiah, who is a graduating electrical engineer. For a company overview, the Naval Undersea Warfare Center, known as NUWC, is the United States Navy's full spectrum research, test and evaluation, engineering and fleet support center. Its focus is submarines, autonomous underwater systems, and offensive defensive weapon systems. Autonomous underwater vehicle, also known as an AUV or a UUV, which is unmanned underwater vehicle, are unmanned and untethered vehicles with limited human assistance in the loop control. Its uses include hydrographic surveys and mine detection. For the project motivation for efficient wireless power transfer, also known as WPT, we had efficient power monitoring with 100 watts to recharge and discharge and trickle charge a battery over time. This would include the recharge and discharge capabilities that we could monitor as the battery was recharging and discharging wirelessly, and its trickle charge capabilities, such as keeping it at 80% power over a period of time. Another project motivation was the fault protection. For fault protection and monitoring, that would be things like the battery heat or the circuit heat dissipation that we do want to turn off and monitor if it got too hot for the circuit so that we didn't damage the components. We'd also want to control and monitor the voltage, power, and current of the system, and then also include safety sensors that could, such as detect water and then shut down, or if it was overheating, it would shut down. The anticipated best outcome is a system that is able to utilize a submerged power supply host platform to recharge a battery on a submerged vehicle in a contactless manner. It was to create an underwater wireless power transfer system capable of charging and discharging 100 watts, and then also show good command and control of the wireless bidirectional power transfer system. The anticipated best outcome, we did not yet achieve our anticipated best outcome. Our current achievements include a 3D printed coil housing design, coil housing assembly, a circuit board assembly, and then we are currently testing the prototype. The summary of our team key technical accomplishments toward achieving the ABO was research on multiple key topics: wireless power transfer, UUVs, batteries, circuit design, coil design, and circuit design. The economic impact for the company included develop cost-effective methods, develop new ideas for developing a wireless power transfer system, and increase company efficiency. This was our block diagram of our wireless power transfer prototype, and I'll have my partner Isaiah explain it a little bit more in detail in the future slides. For my individual technical contributions, I chose the battery and I went with a AA 12-volt DC nickel metal hydride. I chose this battery because it was easy to reuse multiple times. It didn't have just a one-time use. It has less memory loss than other batteries available, and it was environmentally friendly. For the coil design and simulation, Ansys electronics for the simulation, I chose to use a spiral design to be most efficient. Based on other simulations that I ran with different designs, the spiral design was the one that came out on top. The image on the right has a high magnetic field that's shown by red arrows. This is the transmitting coil, and as you can see, there's the red and green arrows that as it gets closer to the center, go upwards and create that magnetic field that would interact with the receiving coil. And then I also went with the spiral design because it was easy to place into the 3D printed housing that I'll explain soon. And then I also did the coil housing assembly, which was the thing that would hold the circuit in place. And then I also collected data in the coil simulations that included the coupling coefficient that would increase, which would be a good indicator of high wireless power transfer efficiency as the distance of the coils was smaller. But this was not a limit in our design, so we could put the coils as close as we were able to. For the coil design and simulation, I used ANSYS Electronics coil simulation to figure out which coil would be the most efficient that we could utilize for a prototype. I constructed the coils for the wireless power transfer that you can see, coil A and coil B, and then I created the wireless power transfer prototype, which was the overall one. I found that the most efficient coil had 29 turns or loops, but because of the size of the 3D printers at URI and the dimensions of the 3D printing coil assembly that I was able to make, I was only able to complete 23 turns. So on the right, the coils that you see are only looped 23 times. I also made the inner radius 50 mm, which was the most efficient simulation that I had found with ANSYS Electronics, which is why our diameter is so large and we didn't have more room to put loops in. Because then the outer diameter, we would have liked to have 84 mm for the outer radius rather for the 29 turns. But again, the outer radius was too large for the 3D print. For the wire that I used Litz wire as it has a reduced skin effect. It's flexible. It's often used in wireless power transfer devices, and it helps prevent electromagnetic interference. And then we also use tape to hold the coils together. We were doing this for the time being as we tested over the air transfer because we didn't want to pot the coils and seal it in case there was any issues with the coils. We were going to use MG 8800 potting material as it would be the best for protecting the coils underwater. But as we said before, we are currently testing the prototype for over the air, and we currently can't put it in the water until we get the potting material. We're also going to use ferrite cores, but they were too expensive, and they help more in preventing interference with the coils and the outside environment. If it was in an ocean environment, say near a submarine, it could interfere or be interfered with the components on the submarine. And we felt it would be more useful in a deep ocean water environment and not just a small fish tank that we were planning on using to test water wireless power transfer. And then lastly, I developed the coil housing assembly. I used Tinkercad for the 3D design, and I had to keep in mind, once again, the 3D printing machine sizes for URI for the dimensions. On the right, you can see the two coil holders that I had made. They're the gray boxes that hold the coils together. And then I had screws you can see on one of the gray squares where I would attach the screws. But before I would do that, I would wedge between the screw and the coil holder a bracket and a small square wedge in each of the screw holes to help structure stability. And the 4 brackets, you could use nuts to quickly loosen and change the distance between the coils, which we're planning on using if we could see wireless power transfer. And then for the dimensions, I used a 240 mm by 35 mm coil housing size. For the screw holes, I did 5 mm by 5 mm with a screw hole length of 10 mm. And then the brackets, or the distance adjusters that you could use to change the distance between the coils, I had a 160 mm by 20 mm bracket with a rectangular hole in the middle that was 140 mm by 10 mm, and the thickness of that was 5 mm. And those were able to make a structurally sound coil housing assembly that could even withstand impact if it fell off the table. And now I'd like to introduce my partner, Isaiah, and his block diagram.
Hi, I'm Isaiah, and this was our project's block diagram. As you can see, we started with a DC input voltage source, which then went to our inverter, which changed the DC input voltage source to an AC source. We created this inverter using a half-bridge gate driver made up of MOSFETs. These MOSFETs are powered by a half-bridge gate driver, which is connected to a controller. And then after that, it is connected to a load inductor and capacitor, which connects to Tucker's transmitting coil. And this is where the wireless power transfer occurs between the transmitting and receiving coil. And this all happens in AC. And once this happens, it connects to the load inductor and capacitor, which then connects to our rectifier, which converts the AC signal back to DC. So we were capable of charging the battery. And then we have a load capacitor and resistor. So we're able to control the voltage and current going to our 12-volt DC battery. Then that you can see at the end is the battery we are trying to charge. My individual technical contributions included circuit design and simulation. When the project began, I took the task of designing the circuit using similar wireless power transfer projects, and meeting with my power electronics course, I was able to design a practical circuit design. To simulate the circuit, I used Multisim. This was a software I had experience with before in labs at URI. I also constructed the inverter and rectifier circuits. I created 2 circuit boards housing each circuit, one with the inverter and one with the rectifier. I also simulated inverter and rectifier circuits in Multisim. I did this to see the effects of the inverters and rectifiers before I had put them in our actual circuit. I also designed and simulated the circuit design. As you can see on the right, that is our circuit design in Multisim. You can see our DC input source. You can see our MOSFET inverter, our load inductor and capacitor. You can see the transmitting and receiving coils in the middle, the other load inductor and capacitor, and then our rectifier full bridge diodes. And then you can see our final load capacitor and resistor. While simulating the circuit in Multisim, I was able to measure the instantaneous voltage and current throughout the circuit. I was also able to run a transient analysis on the circuit so I could see the effect of voltage and current over time. I also constructed the circuit for our prototype. On the right, you could see the 2 circuit boards I constructed. The one on the left contains our rectifier circuit, and the one on the right contains our inverter circuit. I also tested our circuit prototypes using multimeters and oscilloscopes in lab. I was able to test the circuits and compare my results to my simulation results to ensure a working circuit design. Some key acknowledgements. I would like to thank our technical director, Peter Nickerson, for his constant support throughout the year. I would also like to thank Dr. Professor Jiang. He was my power electronics professor at URI, and he was very helpful throughout the course, guiding us with the project. I would also like to thank Brendan Smearbeck, a technical director from URI, for his constant support throughout the project. And I would also like to thank Dr. Sunak, the ELECOMP Capstone Program Director, for creating this great program and giving us the opportunity to work on this for the year. Thank you.